Hello, welcome to numerical ship and offshore hydrodynamics. So, today we are going to discuss how to solve a radiation problem in infinite fluid domain considering lower order panel method, and these are the keywords that you have to use to get this lecture. Okay. So, let us start. Now, what is the physical problem we are going to discuss? We are going to discuss that body is moving of course with acceleration in absence of free surface. So, we assume that the whole domain there is no waves. So, you can consider maybe not exactly the same, but you can consider that moving of a submarine inside the ocean like with some acceleration of course. So, this is the physical problem. Now, mathematical sense what you can say that when omega tending to 0. So, we can approximate very long waves and this can be approximated as there is actually no free surface and therefore, the entire domain we can call as a infinite fluid domain. Okay. So, let us see how we can solve this problem with the help of lower order panel method. Okay. Now, if you remember that first point is to find out the appropriate boundary value problem. Now, here this is the boundary value problem for this infinite radiation problem. Here of course, that governing equation is nothing but this Laplace equation. So, this is the governing equation right everywhere. Now, what are the other boundary conditions? Remember that this is a infinite fluid domain. So, here the free surface is absent. So, therefore, we do not have to apply the free surface boundary condition and also we can assume that the bottom of infinity. Okay. So, there is actually no bottom we can approximate. So, we can omit that bottom boundary conditions. So, also the radiation also is infinity and if you remember our previous videos we showed you like we are dropping something. If I drop something on the water, we can see that in the free surface we can have waves. However, if the body is oscillating inside the domain when there is no free surface, when the body oscillate, the surrounded fluid particle oscillates with the body or moves with the body. The moment the body stopped, therefore, the that water particle also stops. So, therefore, there is no possibility of the radiated waves right. So, there is no point of the radiation condition. So, no waves is going till the till the infinity and die down right. That is what is happening in case of a free surface. If you drop a stone and then this wave got created and slowly it radiated at the infinity. However, in case of infinite fluid domain, the moment the body stopped, similarly the water particle stops. So, really we cannot see any kind of such wave. So, we do not have the radiation condition also. So, therefore, the only condition that we have is the body boundary condition this. Now, what is the body boundary condition? So, if you remember that our kinematic body boundary condition is said that the normal velocity of the body should be equal to the normal velocity of the water particle. Otherwise, what will happen, this water particle will coming out of the body right. I mean, if you remember that I explained that with a simple explanation of this pen with in my hand. If this has different normal velocity, now if the normal velocity of the pen is more than the normal velocity of the hand, what is happening? As long as I move this hand up and this pen is coming out of the surface of my hand. So, therefore, this is something called the body boundary condition and we can say is a kinematic body boundary condition. And if you carefully look into this, we can see that now why it is Nk. Okay. So, let me explain it. Now, the radiation problem also what is the radiation problem? Radiation problem is that you have a body, you are oscillating the body in a calm water. Now, how many ways you can oscillate your body? Now, if you consider this body to be rigid, so let me take this this mobile and I can show you that how many ways you can oscillate this body. So, now this body can be oscillate this mode, which is called the heave. You know, it can move this way, which is surge, also this way, sway, and also we have this pitch, this roll, yaw, everything. So, it can actually oscillate, you can see here it can actually oscillate in 6 different way, right. Now, suppose it oscillate in some mode, let us take heave. So, what would be my the body boundary condition in that case? So, in case of a heave mode, the normal velocity del phi del n in the direction of heave. So, I can write in 3, because if you remember, that is the notation that we are going to use, 1 for surge, 2 for sway, 3 for heave, and so on. And this should be is equal to the velocity of the body in the direction of the normal. So, direction of n 3. Now, for sake of simplicity, I assume that velocity is unit. So, you can assume that velocity is nothing but, let us take 1 meter per second. If we assume this, so definitely you know this equation 2 automatically comes, right, because in this case you assume that velocity equals to 1, right. So, that is why you can see here this equation 2, the body boundary condition is del phi k del n. Now, what is k? Now, is k is defined is 1, 2, 3, right, it is its k is 1 equal to surge, k equal to 2 equal to let us say sway, 3 equal to heave, it could be anything, right. So, therefore, this let us take that k equal to 3. So, that means I am oscillating the body in the heave mode, or I am moving the body in direction of the heave. So, therefore, in that case I can write this del phi del n 3 equal to V n 3. Now, if you consider V is equals to 1, so definitely you can have del phi del n at 3 equal to n 3, right. So, we understand the equation number 2. Now, in case of the moment, how we can write the body boundary condition? Definitely it is r cross n, right. So, therefore, in case of let us take that when the mode is 4, 5 or 6, when you consider that this mode is 4, 5 and 6, then how I could write the body boundary condition. Now, instead the water particle, now see it is, now I can say, let us say del phi del n. Now, let us take it is in the 4th, which is roll, how I can write it. Now, to get this we have to find out that this r cross n, right. Now, you know that it is basically I j k, and you can call it is r x, r y and r z, and then it is, let us take n x, n y and n z, if it is this is so. So, then you can take the component of I is nothing but r y into n z minus r z into n y, and then plus you can take the component of j, this nothing but r z into n x minus r x into n z, and then you can take the component of k, which is equals to r x into n y minus n y into r y into n x. So, this is how we can get. Now, this ith component is nothing but in case of a roll. So, now you can see that it is the first component in this equation. So, basically k minus 3 is nothing but the 1. So, it is nothing but r cross n in the first component, which is the ith component. Now, if you take for the pitch, so then this del phi del n into 5 should be is equal to, it is k minus 3, which is 5 minus 3, which is the second component, that means this the jth component, and then I minus 3 for the EO. So, in this way actually this is moving, right. Okay. So, now this is also clear. So, now I understand fully what is equation 1, what is equation 2 and what is equation 3, right. Okay. Now, the second thing, if you remember, the second part of that, that I listed in the last class, or repeatedly we are one by one we are describing this. So, in the second part is the you have to choose your Green's function. Yeah, it is a third point. Second point is the find out the integral equation. Now, either you can choose your Green's function, that could be also second, that is what I said. So, it is not very strictly you have to follow the thing, you can first choose the Green's function, then you can choose the integral equation. Now, at this moment we are dealing with the source dipole integral equation, right. Now, you see here this part we can call the source, this part we can call the dipole. So, we can call is a source dipole, source dipole. Now, there are other type of Green's integral equation also exists, something called the only source distribution, something called the only dipole distribution. So, what is only source distribution, what is only dipole distribution, that we are going to discuss in the coming days. Now, let us go with the source dipole distribution. Okay. So, this is my integral equation. Now, what about the S? Now, in this particular case, since there is no free surface, there is no bottom surface, there is no radiation surface. So, only surface here is basically our body. So, therefore, this S now considered as the S body. So, I know I have this integral equation also with me, right. I have this boundary value problem, and I know what is the body boundary conditions, and now I know my integral equation also, right. So, if it is so, then this equation 4 can be, if you use this equation 4, you can get the velocity potential at any point on the fluid domain, right. However, to know this, you need to know the velocity potential on the body, because if you remember this integral equation, the right hand side the integral sign is over the body. So, unless you know the velocity potential on the body, you really do not know how to get the velocity potential at any point on the fluid domain. So, therefore, in order to find the value of the source distributed over the body, one must solve the boundary integral equation 4 with the help of body boundary condition 2 or the body boundary condition 3, and that is after the selection of the Green's function. Okay. Fine. So, now let us we take that the choice of the Green's function, let us leave for this moment and let us try to understand what I said graphically. Now, this is phi p is the point anywhere in the fluid domain, this one, and suppose this one is the your body or the ship. Now, you try to find out the pressure of any point over this fluid domain. Now, this whole the whiteboard is your fluid domain. Okay. So, then you need to know the value of all this phi 1, phi 2 etcetera. Now, you can see here I make this phi in order, but it is really not necessary. Okay. Phi 1 could be here and there phi 2 could be anywhere in this surface anywhere. So, So, then however, if you want to find out, you need to know the all these phi 1 to phi 12. Let us say that body I discretize in, let us say that 12 areas, and we can call it 12 panels, right. Then how we can do this? So, we need to apply this integral equation of course, to get this, right. Now, you see here I have phi q. So, I do not know what is the solution for phi q, right. So, in this integral equation, how I can use this integral equation to get this phi, that is phi 1, phi 2, phi 3, that is the actually that is our main aim or goal, right. Now, before further we understand how we do that, let us try to find out how we can get this value at any point phi p with the help of, I mean, for this moment let us assume that I know all these value phi 1 to phi 12. Then how can I get the solution for this particular problem, so that I can get the velocity potential phi at any point in the surface. Now, you see what I do is I replace this integral sign with a summation sign, right. And here we are using the one point Gauss quadrature rule. So, we can say that we are using one point Gauss quadrature. Now, this is the simplest one we are using to understand the concept. So, what I do here actually, I split the whole surface into 12 small surface, and then each surface I place this phi 1, phi 2, phi 3 at the center, okay, or you can say at a centroid. So, I know the location of the centroid also, because I know the exactly geometry of this let us say surface S 1. So, in this surface S 1 I know exactly the location of the phi 1, which is basically center of this S 1, and then at this particular x y z location I know the value of phi 1, let us say I know the value of phi 1, and also at this point I know my this value also, because g is known to me, g is any Green's function. So, if I know the Green's function g, so definitely I know what is the value of grad g dot n, where I know, because if I know my geometry, I know the 4 point and I know how to find out the normal, right. We discussed a lot, you know. So, if I have a quadrilateral panel, I take 2 vector, I take a cross product, I get the normal, right. Again, if you forget this, let me again explain this. So, if this is my panel, so I define a vector over here, let us say A, I define another vector, not here, another vector over here with passing through this corner point, I can call it as a B, and if I take A cross B, I get the normal vector to this surface. So, I know my n. So, entirely I know what is my del g del n I, and also I know my g, because this is that is what I select. Either I can select the Rankine panel method or Rankine that 1 by r, or I can take 1 by r plus h, or I can take 1 by r plus h, which is p, q and t, anything, right. So, if I do that, then the g is known to me. Once g is known to me, this grad g known to me. When the grad g is known to me, I know the grad g dot n. So, del g del n is known to me. Similarly, del phi del n also known to me. How? Because I use the boundary condition del phi del n I is nothing but my n I, right. So, that is the boundary condition. So, I use this boundary condition. So, this part also known to me. So, you can now understand that everything in this equation 2 is known to me, right, provided I know the value of phi I, right. So, this is the idea, this is how I discretize the whole thing, and that is why I called is a one point Gauss quadrature rule, because I assume that all these values actually lies at on the centroid of the panel. So, I am really do not use any Gauss point inside the surface. right. And to understand the concept, I think this is the best way to understand. We really do not go into the numerical complexity, rather like that how I integrate using Gauss quadrature rule, etcetera, etcetera. Let us not go into this. Let us try to understand that very simple way, assuming everything situated at the center. So, value can be get that at the value at center multiplied by the area. So, I can get the value over that panel. So, this is the most simplest way of going with this. Okay. Now, here in this particular problem I am taking that Green's function g is 1 upon r, understood, fine. So, now I have set everything. I set the value for g which is 1 upon r, and also I discretize the integral equation in summation form. So, now only thing I have to find out the way to get this phi 1, phi 2, phi 3 etcetera. Okay. Okay. So, therefore, this further I can now, so once I can take that g equal to 1 upon r. So, now I just instead of I can replace the everything here in the g, and this is basically my integral equation, right. Okay. Now, here actually I replace this del phi del n by n k. Now, I think this is now you understand, right. Here do not confuse with the notation I. So, here you have n k I means what? Now, many people confuse that this k is more than what is I, right. Now, this is idea which is very simple. Now, as I said that this is, let us say, your the domain of discretization, right. See, this is a discretized domain, this I is basically my panel. Now, remember that in case of a reality, if you consider the real ship, let us say, so at each point your this mesh is not horizontal or vertical, it may be some inclined, right. So, in each of this panel your normal is different, is it not? So, therefore, in panel I, let us say panel 1, then your normal, let us say n 1, is not similar to the panel at n 2, that means in second surface that normal is not equal to the first panel. So, in each panel you have actually 3 linear component which is n 1, n 2, n 3, and then you have 3 angular component for the roll pitch and yaw, which is I can say that n 4, n 5 and n 6. So, when I talked about n I n k I, when I talked about this n k I, so I mean that for panel I, right, and we try to find out that which component of the normal you are actually try to find out, because if you oscillate the body in heave mode, so n k should be n 3. If you oscillate or moves the body in direction of the surge, so this n k should be n 1. So, this component n k defines you that which component of a normal you are asking for, and this I implies that it is for which panel, right. So, I think now you understand this, and please do not confuse with this the double notation k and I, because from experience I know that many people got this doubt and they really do not understand that why what is n and what is I. Okay. So, now here also I just write that what is the value for n and I, and what is of course, what is the value for r, right. Now, here this x g, y g, z g, right, is basically the center of gravity, and xi, eta, zeta is basically the panel centroid. So, now you understand the definition for r also, right. So, what I said, let me write here again. Suppose this is your body and this body has a global C g, and that global Cg is nothing but your xg, yg and zg, and if you do the paneling. So, this panel, this centroid it is xi, eta and zeta. Okay. So, this is the difference. So, these are the common notation that we are going to use, and in future you also understand these very well, like because otherwise how we can do the Rx in R cross n, right, if you do not have the information about what is your global Cg, right. Okay. So, let us try to find out that value of del G del n and the value of okay, let us find the del G del n first, and then del phi del n I we already actually we know. So, we really do not need to discuss about how I can get this value for n I. We have already discussed value for n I before. So, we really do not discuss now, but we need to discuss about the del G del n. Okay. Now, in fact, that is also we already done it, we solved one problem. From that problem we have defined many things, right. So, now you know that what is del G by del xi. Now, if you remember that we already done it in I think last class or last to last class, right now I do not remember, but we have done this for r square equal to x square plus y square plus z square, and then we find out that that let us say that now in this case here again that del r del x equal to, in that case this is 2x something like this. Now, here instead of r, now if the r square equal to x minus xi square plus y minus eta square plus z minus zeta square. Now, if you differentiate with respect to r, so we have 2 r equal to 2 into x minus xi, and then it is del xi del I, so it is minus 1. So, now I have okay, so there I miss, right, into del xi. So, I know that del r by del xi equal to now x minus xi divided by r. So, it is, and now we have the minus 1 with this. Now, this actually we have already done, right. Now, similarly if you now differentiate del G by del xi, now del G by del xi you have to do it del r of 1 upon r and then multiply by del r by del xi. Now, del r by del xi it is minus x minus xi by r, and then that it r 1 upon r, if you differentiate it is coming out to be this 1 by r square, right. Okay. So, now you replace this. So, this is your 1 by r square, and then you have x minus xi by r. So, then you have this multiplied by the r, and in together you can get this value x minus xi by mod of r cube. Now, here since I have already done this, so I really do not do much over here. So, I will request you try to do this by your own. It is nothing, you have to use this the simple thing, this capital R square equal to x minus xi whole square plus y minus zeta whole square plus y minus zeta whole square plus z minus zeta whole square, and then find out del r by del xi, and then you use the chain rule, and then you can get this value. Okay. Now, similarly I can make that del xi del eta equal to y minus eta by r cube, and del xi by del zeta equal to z minus zeta by r cube, right. And then this del g del n is nothing but r dot n divided by r cube. Okay. So, now I have this value for del g del n also. So, let me now again replace over here. So, if I replace over here, I can get alpha p equal to phi p I equal to 1 to 12. Now, phi I equal to r dot n I by r cube minus 1 upon r I into n I k dot d a, right. So, everything here is known apart from the this value of phi I. So, how to get this value for phi I? So, this is the main problem. So, today let us stop at this point, and from the next class onwards we are try to find out how do I get this value for phi I. Okay? Thank you.